Hello and welcome the first H2Marine training webinar. My name is Michael Bambau. I'm researcher at the Center for Research Technology, LAS, with the short acronym CERT. Today we will have our first online training webinar with the title Accelerated Stress Testing for PEM Fuel Cells, Maritime Applications with Multichannel, Potentiostat, and Multi-Single Cell. This is the first out of the four training webinars that we will organize within the H2Marine project. Before starting with our webinar, let's have a first overview of the H2Marine project. The H2Marine project is a project funded by the Clean Hydrogen Partnership and the Swiss Secretariat for Funding, and it started in 2024. And we have ahead of us 1 year more, and we have 13 partners from 5 European countries. And the objective of this project is to design, build, test, and validate 2 PEM stacks generating 250 to 300 kilowatt electric power for maritime applications and for a modular scale-up design. The H2Marine consortium is comprised of partners from Greece, Switzerland, Germany, Sweden, and Finland. We have 2 stack manufacturers, PowerCell Group and EH Group. We have also partners from Germany, TKMS, Dana, ZSW, University of Freiburg, and Greenerity. From Switzerland, we have EPFL Beyond Gravity, and also from Finland, VTT, who will be also organizing this webinar. And from Greece, we have Klube, who is the dissemination leader, and Kleos, who represents the Greek maritime industry. It's a first overview of the H2Marine concept. What the H2Marine project includes is, first of all, the definition of the end user needs, the maritime environments, and the test requirements for the 2 stacks, and also test different diagnostics for the stack and the overall system in order to prognose and diagnose the health of the critical components of the system. And then we have the design, the construction, and the validation of the 2 PEM fuel cell stacks, which will generate up to 300 kilowatt electric power. Those will be tested in a relevant environment. After that, we will design the concept to upscale those stacks into megawatt and multi-megawatt systems. And of course, we are going to implement and assess the techno-economics and the environmental feasibility of those solutions. Targets of the H2Marine are fully aligned with the targets by the Clean Hydrogen Partnership and the Clean Energy EU. So those include the testing, the design and the building of the 2 stacks, the diagnostics and the testing of those, the design of scalable concepts that can lead up to 10 megawatts by 2030. Stack lifetime is also a very core pillar of the project to achieve 40,000 to 80,000 operational hours, and also cost efficiency, which is very important to achieve the targets by 2030. So I'm pleased to announce our 2 experts that will be presenting in this webinar. Amina Alimbekova, a research scientist at the VTT Technical Research Center of Finland, and Dr. Jari Ihonen, principal scientist also from VTT. And the topic is a very hot topic in PEM fuel cells, which is about accelerated stress testing for PEM fuel cells in maritime applications with multi-channel potentiostat and multi-single cell. So without any further delay, I would like to give the floor to our 2 speakers. Start the presentations. Thank you very much.
Yes, thank you. Hello, everyone. I'm Amina Alimbekova, a research scientist from VTT Technical Research Center of Finland, and I will be talking about the the project we have developed within the H2MARINE about accelerated stress testing for PEM fuel cells in maritime applications with multi-channel potentiostat and a multi-single cell for high throughput testing. And I will be talking about in general first, the accelerated stress testing for PEM fuel cell development, the maritime ASTs, the issues and the relevance within the project and the PEM fuel cell development as a whole, then a little bit about the selection between hydrogen air or hydrogen nitrogen ASTs, and then we'll go in detail about the measurement setup that uses the multi-single cell, what it is, the multi-channel potentiostat, and then combining them to make to measure high throughput AST campaigns. Then we'll go into the results and the conclusions. Yes, so to begin, let's establish the framework for the accelerated stress testing in the context of PEM fuel cell engineering. As we know, the standard long-term durability testing are time-consuming and quite expensive. So to mitigate this bottleneck, accelerated stress tests are applied to the system to operate it beyond its nominal conditions to accelerate the specific degradation modes. And in PEM fuel cells, these primary stressors that govern the degradation include voltage magnitudes, voltage transients, temperature fluctuations, relative humidity fluctuations, and the gas environments that the system is exposed to. By strategically combining the stressors, we can isolate the the distinct electrochemical phenomena that describe the degradation. For instance, the catalyst degradation is primarily proceeds via two mechanisms within PEM fuel cells: the platinum dissolution and migration, or platinum particle coarsening and growth via oswald ripening. And because these two phenomena are quite dependent on voltage magnitude and the frequency of the voltage transients, we can basically combine the repetitions and the voltage magnitudes to simulate the load variations, coupled with elevated temperatures or high relative humidity to kind of look at how the electrochemical surface area decreases over time. And understanding how to tune these variables is what allows us to design the targeted protocols, which brings us to the two primary design strategies for the accelerated stress tests. And when designing accelerated stress test protocols, the main methodology generally follows two strategies: either a component-driven strategy or operation-driven strategy. And component-driven strategy on the left focuses on isolating the degradation of a specific material layer. The component itself dictates the test parameters for the AST. For example, to isolate catalyst degradation, we would probably apply some voltage, like potential cycling, as shown here in the table from the Department of Energy catalyst AST. But then if we want to study carbon support corrosion specifically, we would then expose our membrane electrode assembly catalyst to very high potentials or reverse current decay conditions that severely accelerate the carbon support corrosion, the structural collapse, and then subsequent electrochemical surface area loss caused by platinum detachment. Also, it could be done under low relative humidity to further kind of exacerbate the conditions. And the standard protocols, like Department of Energy Catalyst AST, Carbon Support AST, and Membrane AST, are kind of the classic examples of this material or component-driven approach. And then we have the operation-driven strategy, where we shift the focus from an isolated material to a system level, where here we define the protocol defined by its real-world operational events, such as simulating the start-stops, procedures, high power demand times or prolonged idling phases. And in this workshop, our focus and webinar, the AST that we developed kind of bridges these two strategies. And as we look towards the maritime applications, the operational profiles require a unique combination of long steady state holds combined with the transient stops. And when we talk about the maritime ASTs, we must address a critical gap in the current literature and also fuel cell reliability engineering, that ship is not a car, and we cannot just apply the automotive ASTs or apply durability results from the automotive ASTs to maritime ASTs. Because the vast majority of operation-driven accelerated stress tests that have been developed in the recent years, such as the US Department of Energy AST protocols or the ID-FAST projects in EU, were developed specifically to mimic the urban road vehicles. And if we apply these to the maritime PEM fuel cells, we're risking generating inaccurate lifetime predictions. And as we can see from the data here, the context is fundamentally different between the automotive and maritime fuel cells, primarily across three main operational features, which is the start-stop frequencies, the kind of baseline load profile, as well as the nature of the transients themselves. First, let's consider the start-stop behavior. In automotive systems, the start-stops occur several times per hour due to traffic or short trips, but in maritime vessels, they undergo long, continuous sailing missions where start-stops are quite rare. Then, even when ship docks at the port, it still requires some amount of power for cargo handling, for maneuvering, and this constant demand minimizes the time the fuel cell resides at the idling or open circuit voltages, which are both very meaningful degradation drivers for automotive tests. But also the scale of maritime systems, because ship could be bigger than a car, we can allow active engineering mitigation strategies on board, such as nitrogen purging during shutdowns, which fundamentally changes how degradation occurs in the catalyst. Then let's look at the transients. So in automotive applications, the dynamic load changes are quite rapid due to braking and acceleration, and it accounts for over 50% of the performance loss. But in maritime systems, cruising phases are characterized by low and stable power demands, especially in case of hybridized systems with battery storage on board. But in the maritime systems, when the transients occur, they're quite massive, mainly due to external influences. For example, the wave situation in the water, the hull fouling, basically how much biomass is on the biofouling is on the ship, or cargo distribution inside the ship, or the extent of the maneuvering. The vessel power demands can fluctuate up to 40% of its nominal power in less than 10 seconds in those conditions. And this tells us that maritime fuel cells face quite different distribution of stress factors compared to automotive systems. And because these unique profiles govern the degradation, we cannot really apply the same AST profiles to assess our lifetimes for maritime PEM fuel cells. But at the same time, we need some methodology that can mimic these maritime specific profiles quite efficiently without bottlenecking the research and development. And these requirements form the motivation for the high throughput methodology that we have developed in this project. Now let's look at the choice between hydrogen air or hydrogen nitrogen ASDs, because during real-time operation, it will be working under hydrogen air conditions, and the stresses in these conditions are dependent on different stress variables. And if we run a maritime dynamic profile using a short stack with the hydrogen air feed, the degradation we see is quite complex. And because the current distribution is different across the stack, the local relative humidity fluctuates, and you could get local reactant starvation or flooding in on the electrodes. And in short, it could be quite difficult to isolate why exactly the catalyst is failing. Is it from the voltage transients, or is it from the kind of the mass transport limitations on the catalyst that could be reversed? So in our case, we decided to use a hydrogen-nitrogen atmosphere as a specific tool to decouple those overlapping stressors. And when you're running a test under hydrogen-nitrogen conditions, hydrogen on the anode, nitrogen on the cathode, the ohmic resistances become negligible, the transport losses disappear, and the cathode potential becomes equals to the cell potential. So this creates idealized but uniform electrochemical environment. And then if we use the voltage transients from some maritime drive cycle onto a hydrogen-nitrogen environment, we're basically combining this component-driven ASD strategy to isolate the influence of the kind of maritime profile with the operation-driven maritime profile. Then we can map exactly how the maritime voltage swings affect the state of health of the catalyst, how they drive platinum dissolution, or for example, carbon support corrosion, completely independent of the water management issues and gas distribution problems. But of course, to validate this complete picture, we eventually have to cross-reference our findings with the real-world hydrogen air conditions. But as a reference here, the Astudillo and Gasteiger paper pointed out that when moving the AST protocols from hydrogen air to hydrogen, from hydrogen nitrogen to hydrogen air atmospheres, it requires adjustments, particularly modifying the cell voltages to account for ohmic resistances, which would be different depending on the state of the system. As well as I will be discussing shortly with our multi-single cell stack, running at high overstoichiometry to ensure perfect reactant distribution, which is not really a case with the real fuel cell systems. So to execute the ASTs with using maritime profiles, we use a hardware configuration shown here. And this is our multi-single cell, which is a short stack. And historically or traditionally, the durability testing kind of forces you into a choice. You either test single cells sequentially, which takes a long time, and then also the environment could be different depending on the measurement time. So it introduces this kind of this environmental drift. Or you can test inside a short stack. The issue with the short stack is that the cells are dependent on another. All of them are under the same conditions, same kind of forces are on the cells, and the failure in one cell can result in skewed flows or current distribution in other cells. And this is particularly the case under hydrogen air conditions. And as you can see from the 3D models here and also the physical photographs later, the multi-single cell addresses these limitations by offering this kind of dual mode where you can use it as a 8-cell stack or 8 single cells. for high throughput screening of the independent MEAs using a shared mechanical fixture. And as you can see here on the picture, when operated in this multi-single cell configuration, it gives us a very big methodological advantage where we have a consistent experimental history within the stack. Because all 8 cells are integrated into the same block, they share the same fuel supply, the kind of the air composition or nitrogen composition, the same relative humidity parameters, and the exact same thermal environment. And any macro level variations in the test bench will affect all the cells uniformly. And therefore, if some kind of disturbance occurs during a 100-hour maritime cycling run, it will affect all cells evenly, especially under hydrogen-nitrogen mode, because no water is being produced and the flows are selected to be strong enough to not cause any flooding. And by fixing these environmental variables across all 8 channels simultaneously, we can isolate these experimental variances to the components themselves. So if there's some variation in the MEAs, it will show more prominently. And since we are isolating each cell from each other's, making them kind of as single cells, we cannot use the standard single load to connect kind of all cells, to use this as a stack, because we want to run independent profiles to each individual cell to track individual degradation rates. And therefore, we need a specific technology that a solution that we will look at next. So if we use a single standard electronic load, we would have to use it as a, or even like a single potentiostat, we would have to use it either as a single stack or as a, or in sequence with multiplexer. But multiplexing is a major bottleneck because basically it forces you to measure each cell in sequence still. And we lose a lot of either data because if all of them are running, we can only capture the data in sequence, or we're losing time because we treat each cell individually. And to kind of avoid this limitation, our methodology uses a dedicated multi-channel potentiostat, which in our case, it's the PalmSense multi-MStat for the high-range system. And in traditional electrochemistry, the multi-channel potentiostats are used for small-scale combinatorial screenings, the catalyst ink research, or microelectrode array research. But here we're applying them on the full-scale membrane electrode assemblies, 23 centimeters squared. And the advantage of the system is that it houses 8 independent potentiostat into one unit. So we can perform measurements across all 8 cells simultaneously. And these channels don't have to run the same protocol. We can run kind of the same protocol throughout all channels simultaneously, but then we can also program each channel to run a different cyclic program under hydrogen-nitrogen atmosphere. And by using this multi-channel potentiostat with the multi-single cell, we create this unified testing platform that can screen through 8 MEAs and give us data for from 8 cells simultaneously. And this is what our physical setup that we have developed looks like. So we have the fuel cell test station that is controlling the gas and the thermal conditions for the multi-single cell. And each of the cells is connected to the multi-channel potentiostat channels. And then we have a PC that controls the fuel cell and the multi-channel potentiostat and gets all the data. Now we have reviewed the testing platform. Let's look at the exact protocol that we have used. As discussed, the real world maritime duty cycles are quite complex and they introduce the multi-stress degradation environments. But to isolate the pure platinum catalyst degradation from overlapping issues like carbon support corrosion, we have decided to use the hydrogen-nitrogen environment and remove completely oxygen from the anode and maintain the potentials at the values below 1 volts. We can suppress carbon corrosion. And this electrochemical window between 925 millivolts and 775 millivolts kind of gives us the window where we can look at the voltage-driven processes, such as the platinum oxide formation reduction cycles, platinum dissolution, particle coarsening, and so on. Using this approach, we have developed these 2 distinct AST protocols. That were applied for 2 different separate batches of MEAs. Here you can see the AST sequence for voltage hold, where we have mimicked the kind of the log steady state runs at different voltage values. And this is to track the catalyst degradation under constant voltage stress. And then the results from the voltage hold AST give us a suggestion for the upper potential limit that is used for the next cycle, which is the hydrogen soak, short stop, and shutdown ASTs, which are meant to simulate the frequent short operational stops and the automated shutdowns that occur less frequently throughout the maritime system lifetime. And this is to capture the rapid potential excursions or transients that the catalyst experiences during the short stops or shutdowns. And we were running these protocols and the approximate sequences shown here in the flowchart. We have generated a data set to validate our testing setups capabilities. And let's now look at the results of the degradation tests. So as we established, the steady state voltage holds within the electrochemical, like within this window between 925 and 775 millivolts, is designed to mimic these maritime idling conditions. And in the literature, PEM fuel cell operations below 0.8 volts is considered safe for a platinum catalyst, but the operation above 0.9 volts is known to trigger the catalyst degradation. And our platform, like the testing setup, allowed us to map the kind of the influence of this holding voltage on the degradation by running all these tests simultaneously. And as you can see from the electrochemical surface area versus time plot, we can see that the electrochemical surface area loss ranges from 13% to 23%, very dependent on the applied voltage. And then if we look at the early stages of the accelerated stress test, basically beginning of test to the first middle of test, we will notice that the degradation rate increases significantly once the holding voltages are above 825 millivolts. So they kind of divide into those 2 groups. And this gives us a first hint that exposing the cathode potentials to elevated voltages is the primary kind of voltage-driven catalyst degradation during the ship idling phase. Another finding that we can see from here is that long-term kinetic trend. So after the 735 hours of exposure, the electrochemical surface area curves do not reach a plateau, suggesting that it's in the early to intermediate stage of its degradation. This basically shows us that using our multi-channel potentiostat and a multi-single cell, we can successfully monitor the potential dependent catalyst degradation across these long times. Then we analyzed further the degradation rates across the testing intervals. So we plotted the degradation rates versus the holding voltages, basically the slope between the beginning and the middle of tests and then end of tests. And this data shows that there is also a clear time-dependent slowing down of the electrochemical surface area loss, where in the initial stages of the accelerated stress test, the degradation rate is quite high, and then it slows down and then becomes more or less even across all voltages. But we also can see that holding voltages at 0.85 volts and above have higher degradation rates than the rest. And this kind of shows us this window where the degradation shifts from a little slower to accelerated degradation mode. And below 825 millivolts, the degradation proceeds a little slower, and here the aging assumed to be dominated with the kind of very early stage platinum dissolution. And as voltage increases, the degradation accelerates, and Oswald ripening or particle coarsening increase, and the platinum crystallite size will also increase, as will be shown with the XRD analysis next. And these kind of kinetic insights give us a justification for using the 825 millivolts as the upper potential limit for our subsequent shutdown protocol. And by placing our limit at this voltage value, we kind of ensure that our baseline degradation is slow, so we can isolate the impact of the actual transients themselves without kind of inducing more degradation from the high voltage holds. Let's look now at the short stop and shutdown degradation. And these are, on this slide, we have the electrochemical surface area versus the time for each kind of dwell time. So held for 1 minute, then the transient happens, held for 1 minute at the lower potential limit, and then so on. And as you can see, from the curves, the platinum surface area loss is quite sensitive to the frequency of the short stop and shutdown events, where the high frequency short stops at 1 minute and 5 minute holds dwell times showed the largest and the most aggressive electrochemical surface area loss. And in this test matrix, the total time spent at the upper potential limit at 825 millivolts is exactly the same across all frequencies at half the time, so 192 hours. And because the absolute time spent at the upper potential limits are the same, it means that the transitions, like the rapid and frequent voltage transitions themselves, give the most degradation to the platinum catalyst. And this kind of provides the conclusion that under maritime shutdown conditions, the catalyst degradation is also governed by the number of those voltage transients rather than the time it spends at these high voltages or upper potential limits. Because each excursion, so each voltage transient, triggers the oxidation reduction cycle that accelerates the kind of platinum loss. And furthermore, to further highlight the importance of the testing setup that we're using, let's say we're measuring these in sequence, the minor environmental differences in temperature control, in gas purity, or it can kind of mask this effect or not show it to the full extent, which kind of shows the benefit of measuring all of them at the same time to run them simultaneously with the identical environmental history. And then when we again quantify the degradation rates versus the shutdown frequency or number of stops per 24 hours, so 1 minute the shutdowns are more frequent, we can see first that at higher shutdown or frequencies, the beginning of test to middle of test degradation rates are higher than the beginning and end of test. And for the slower, the degradation towards end of test is higher than in the first half of the test, basically suggesting that for the slower lower frequency cases, the degradation again is in its kind of early stage, where the fresh catalyst layer, like the catalyst layers, has very small platinum particles which are unstable with high surface energy, and then it kind of gives this big electrochemical surface area loss in the first, like in the beginning, compared to the more frequent cases where they're already towards the like mid to later stage where they're already coarsened into larger crystallites. And basically, and then talking about the crystallites, we performed the XRD analysis on the with our colleagues at CERT on postmortem XRD on our aged MEAs as well as the fresh MEAs. And as expected, the crystallite size increases with increasing voltage hold of magnitudes, as well as with increasing frequencies of the short stops or shutdowns with 1 minute and 5 minute cases. So basically, especially when looking at the short stop and shutdown AST data, the coarsening here is probably driven by the oswald ripening, by the oxidation and reduction cycles, and it reduces as the amount of these cycles is smaller and smaller. And when we compare the voltage hold and the short stop and shutdown side by side, we can see that both have this threshold behavior. So basically the difference, but the stressors in those cases are different, because under the steady state conditions, under the voltage hold, we observe as kind of this limit at 825 millivolts, above which the platinum dissolution occurs quite rapidly due to enhanced surface oxidation. And then under the dynamic condition, the short stop and shutdown, the frequency threshold emerges at the kind of faster timescales at the 1 minute and 5 minute dwell times, where the repeated stripping of the oxide layers drives the faster dissolution. And when the shutdown occurs at kind of larger timescales, the degradation slows down. And the most critical engineering takeaway from comparing these two modes is that while it is important to identify the safe voltage limit, it is probably not sufficient to avoid or to reduce the electrochemical surface area loss, because the repeated and rapid voltage transients at 1 minute dwell time over 384 hours produces equivalent surface area loss during the 735 hour at 925 millivolt voltage hold. So basically, the transients themselves are more aggressive and lead to faster surface area loss compared to even very high voltage holds. But to be fair, these 1 minute holds, 1 minute short stop cycles are quite, and they're unrealistic and represent kind of the worst case scenario. But in real time maritime profiles, these probably will occur on hourly or daily scales. So in terms of when we're comparing these 8-hour and 12-hour cases, it's consistent. It's equivalent to the holding to the electrical surface area loss when we're holding at lower voltages. Therefore, for practical maritime application, fuel cell application, we need to kind of, in order to maximize durability, we must minimize unnecessary voltage transients while keeping our upper potential limit at like a modest values. And as we wrap up the technical portion, let's discuss some like limitations of the current methodology. First, within the measurement setup, we have used 2 distinct MEA batches. For the second one, we used the lower loading, which lower loading will magnify the kinetic overpotential during the polarization curves, basically meaning that kind of the lower initial platinum loading will reduce the kinetic capacity of the platinum of the catalyst layer. So the equivalent loss of electrical surface area will probably trigger higher voltage overpotentials in the during the polarization curves. And while this variance kind of limits the qualitative alignment of our values, the normalized degradation trends are quite consistent, as well as when comparing the crystallite growth with the postmortem analysis. Then our intentional choice of hydrogen-nitrogen atmosphere during the accelerated stress tests makes the frames the whole study to be specifically voltage-driven catalyst, voltage-driven catalyst mechanisms. And in the real world, hydrogen-air maritime fuel cell operation is complex. It will have overlapping degradation modes that will probably influence each other and contribute more can contribute more degradation together than separately. And the true degradation rate can only be measured when all stressors are combined, and this should be measured separately. And then also we must address the thermal dependencies, because when used under hydrogen-nitrogen, the thermal profile of this the stack is quite even, and then compared when the fuel cell stack is running under load. And we have isolated the kind of voltage and frequency effects under static 75 degrees. In an operational stack, the temperature is current density dependent, and active cooling before shutdown, which could be kind of an engineering strategy to reduce the degradation, will also change the kinetics of oxide formation and the oxidation reduction cycles. And finally, to conclude everything, we are presenting this first use of multi-channel potentiostat with the multi-single cell to produce AST data, 8 cells worth of data simultaneously. And this was used for independent AST cycling of multiple single PEM fuel cells. And this parallel high-throughput degradation testing allows direct comparison of the membrane electrode assemblies or AST profiles. And this novel setup now is at VTT will be used for efficient catalyst aging studies or AST studies in the future. Yeah, thank you so much. I'm open to the questions. You can put them in the chat or ask them from here. Thank you.
Thanks a lot, Amina, for the very interesting presentation and also the results that are really important to draw some conclusions also on how to operate the fuel cell. I'd like now to invite everyone to write in the chat questions. We have 10 minutes to answer them. So when now that we wait for the questions, I have one let's say more broad question for you. And we know that the maritime sector is complex in terms of the different segments. For example, it's different to design a fuel cell for a river vessel rather than a deep sea vessel because of all the transients. So based on your results, which operational strategies should be prioritized in order to reduce degradations in the fuel cell? It's a more generic, let's say, question.
Well, kind of based from the results, we can see that the transients are what drive more accelerated degradation profile. So anything that includes rapid transients should be avoided or kind of reduced, where the kind of the magnitude of the transients, so the voltage window between the transient where the transients occur should be smaller. So, for example, it could be voltage capping, so that could reduce the magnitude of the voltage transients. So, but in terms of the operational modes, I have a hard time imagining that some operational modes can be avoided completely. Like you cannot make the ship not maneuver or slow, or like shut down, to have shutdowns or short stops. It's more about how you deal with them. So again, the nitrogen purging will help compared to just hydrogen air shutdowns. Hydrogen nitrogen shutdowns will probably reduce the amount of platinum degradation or carbon support degradation. And then also the kind of voltage capping and the other engineering, like system level mitigation strategies are what I think will solve the degradation issues.
Very important to design BOP components accordingly, match the skills requirements and the degradation, to reduce degradation also very important. So I don't see any questions. So there is one question. Maybe you can write it in the chat. And
hello. Can I
hello.
ask the question directly? Otherwise, I have to write a lot, taking up 10 minutes time. Thomas Bayer, Lloyd's Register. Thank you very much for the very interesting presentation. If I understood the AST principle, you're basically separating any influence from other aspects beside the load transients. So basically the voltage changes between your operation profile. In a real world operation of a fuel cell, we have wet dry cycles, we might have flooding due to inclination on the ship, for example. You could have theoretical air or fuel starvation. So basically having various degradation mechanisms simultaneously involved and impacting each other. So how would you see the accuracy of your AST compared to a AST which has more factors involved?
As I mentioned before in the kind of the limitations section, the true degradation, like the true degradation extent will be assessed through these ASTs with more components that include the different degradation drivers. So in our case, because it's just voltage-driven degradation, it can only show the influence of the kind of, for example, the during flooding, there could be some voltage transients, and this kind of is just a component of that. So I wouldn't say it's completely accurate and will predict the very accurate lifetimes, but in terms of just voltage transients and the influence of the voltage-induced degradation for platinum catalyst specifically, it could be quite useful, specifically for maritime. If we design more accurate maritime accelerated stress tests. Yeah.
Okay, thank you.
Yeah, may I comment? It was an excellent question, and we understand fully that you have to combine all the stressors because these are affecting each other. But at the same time, you would like to quantify one stressor very accurately, that you know that how to mitigate that one, and that is our goal.
Okay, thank you.
We have time for one more question. If there is one in the audience. If not, want to thank you for first of all the presenters, Amina, for this excellent presentation and very informative. And I would also like to thank the audience for attending this webinar. We have also more webinars and training tutorials coming up in the next until the end of the year. So please stay tuned. Also, you can be updated about our activities on the H2MARINE project from our website and from our LinkedIn page. So thank you very much for attending, and thanks also to the presenters, and then stay tuned for a new update for the project. Thank you very much.
Thank you.
Thank you, everyone.
Thank you.
Thank you. Bye-bye.